morning, everyone. So, as the chairman already said, my talk will be on modified Poisson equation in a field gravity. So, the main goal of this is to understand how the gravitational field is the gravitational field relationship with the matter distribution is modified by this theory. So this is a preliminary step into other things I want to do next, which are to apply this for stars and try to compare it with the available data in order to test this theory of gravity. So this is the outline of my talk. I will briefly start by introducing the geometrical trinity of gravity. Then I will talk about the extension of one of the theories of the trinity, which are the alpha field theories. Then I will apply the weak field limit to that theory and obtain the Poisson equation. And finally, resume my talk. So we know from general relativity that there is a relationship between geometry and the gravitational interaction. Specifically, in this case, the gravity is tethered to the curvature of the space-time. So there are some tensions in the theory that still need to be fully understood, and that calls for the extension of the theory, and there are many ways of doing so. I'm not going to focus on that today. Instead, I want to focus on another question. This needs to be the only way we look at gravity. And it turns out that it's not. So just recapping a little bit, in general relativity, gravity is related to the curvature of the space-time. And in that case, space-time is curved, torsionless, and metric compatible. And just to be very clear, in my notation, this over ring here represents that I'm calculating things with respect to the Relativity connection. So the second way would be to consider that your space-time is flat and metric compatible, and thus in this case we have torsion. And this is exactly what is done in the so-called teleparallel equivalent of gravity. The third interpretation would be to consider that your space-time is flat and torsionless. So in that case, we have what is called non-metricity, here Q, which I will explain a bit more later. And we have what is so-called the symmetric teleparallel equivalent of GR. So going a bit further on those two concepts, in the teleparallel gravity here, we have torsion, and in that case, the fundamental object is the connection, while in GR, the fundamental object was the metric. We have a connection, but it's the Relativity connection, which also depends on the metric. And in that case, we can interpret the torsion with this image. If you have two vectors and you parallel transport them along each other, and the parallelogram doesn't close, then we have torsion in your space-time. And torsion measures exactly that. Now about the non-metricity. In that case, we have the metric and the connection as the fundamental objects, and this is going to be a bit clearer, more clear later. So the interpretation of non-metricity is that if you parallel transport a vector along a curve, and the length of the vector changes while you do so, you have non-metricity in your space-time. So to focus a bit more on the parallel gravity now. So the torsion is defined as this difference here between the connection. And in this case, it's not the Lane-Emden connection anymore. Instead, we have a connection that is formed by the Lane-Emden connection plus this extra term, which is called contortion. And by definition, the torsion is antisymmetric in the last two indices. So in that case, I can construct only one trace, and to construct one scalar, I need to contract it with itself because it has three indices. So in that case, I have three possible contractions here, given by these three terms, and this specific definition of torsion scalar is very interesting for us because it's related with the Lane-Emden scalar by this equation. So you can see here that the difference will be just this total derivative term. And this will be important later on. So now we can define the action for the teleparallel gravity. We have the torsion scalar here instead of the curvature scalar. And it turns out that it's more suitable to use the tetrad formalism instead of metric. And in that case, you have polarity of action with respect to both the tetrad and the connection. So variation with respect to tetrad gives this equation, which although doesn't look very familiar, it's exactly the Einstein equations. Because everything that's here in the left-hand side for you is equal to the Einstein tensor. So nothing new so far. Now as for the connection field equations, we have this set of equations which are identically satisfied. This means that I can choose my connection quite freely as long as it is flat and metric compatible. So now moving on to the symmetrical parallel gravity, which is with respect to non-metricity. The non-metricity is defined as the covariant derivative of the metric, so that's why we have both metric and connection as fundamental objects. And in this case, this covariant derivative is not related to it anymore, but with respect to a more general connection. And that's why this term, this non-metricity in general, doesn't vanish. So in reality, what the non-metricity measures is the failure of your spacetime to be metric compatible. The connection in this case will be a combination of the Lane-Emden connection plus this extra term which we call disconvection. And by definition, the non-metricity is symmetric in the last two indices. So we now have two possible traces, which are given by this expression. You can contract it either the second and third indices or the first with the other two. Again, we have three indices, so we need to contract it with itself. And there are actually five possible contractions, but here I have just four. Because this specific definition gives me this relationship with the Lane-Emden scalar. Quite similar to what happened with the torsion scalar. So again, we have this extra term, which is a total covariant derivative with respect to the Lane-Emden connection. Now we can define the action for the theory, which will be this one with Q, and vary it with respect to both metric and connection. The metric field equations are this, and again, even if it doesn't look very familiar, it's actually equivalent to the Einstein field equations. Now for the connection equations, we have something very similar to what happened in the parallel gravity. The equation is trivially unsatisfied as long, so you can choose connection freely as long as it is flat and torsionless in this case. So keep that in mind because I'm going to go back to this later. So there we have the trinity of gravity, three different theories describing the same thing. And we say that they are equivalent because as long as we talk about equations of motion, they lead to the same results. And that's because the scalars of the theories are related to the Ricci scalar just by a derivative. So now I want to move on to the generalization of this theory, the symmetric parallel equivalent of gravity, because I want to explore the modified theories of gravity, and in this case we are still in GR. So for the f of q...
May I ask a question?
Yeah.
So do we have also metric tensors in the other two cases of those?
Yes.
Yeah, so what are those? What is that metric tensor?
It's the same. You mean?
I see, it's the same.
Yes. So now for the f of q theories, I need to generalize the action to allow for nonlinear terms of q. And again, I need to vary it with respect to both metric and connection. For the metric, now I wrote in a, let's say, better way. So you can see here that we have the Einstein tensor. So all the rest of the other terms and this fq multiplied here are coming from the modification of the theory. And in that case, if you say that f is equal to q, then this term disappears, and this becomes 1. So you come back to general relativity. Now for the connection field equation. Since I have this extra term here, I can no longer have the luxury of freely choosing my connection. Now I needed to satisfy this equation. And as you noticed, I put here a red box because these are the most complicated set of equations. It doesn't mean that these ones are less complicated, but they are less complicated, but it's still complicated. But it turns out that there are ways for us to determine which connection components we have. So for that, I'm going to assume that my metric is static and spherically symmetric, and that the connection has the same symmetries. And moreover, I need my connection to be flat and torsionless because this is a requirement of the theory. So when we do this, we get two solution sets possible, and the second solution set actually has two branches of solutions. And I'm going to focus on the second one because it has a proper encompassed limit. Now, after all of that, this is how the metric equations look like. So you have here in the first bracket what would happen in GR, and all the rest is the modification of the theory. And for the convection field equation, I end up with just one, this one, which is satisfied by a rather simple connection choice. And in that case, we also have a constant limit, so everything is consistent. Now I want to apply the weak field limit, and for that it's better if I rewrite this equation to have it like this. So I have the Isaac tensor separated from the other contributions of the modifications of the theory. And I can rewrite it again to obtain this relationship for the Ricci tensor and the energy momentum tensor, the W tensors, and the traces. So now when I apply my weak field limit, I know what to expect from here. It's the same as GR. I just need to worry about these extra terms. And here as well, I will have the same as GR. I assume that the fluid is a perfect fluid for simplicity. And I take only the terms up to second order in velocity. So it will look like this. I will have only this and this terms, and these ones will be neglected. So as for the extra terms, modified terms, I will have up to the fourth order, so they can be neglected as well. And I will further assume that my metric has this form here. So at the end of it, I get this Poisson equation, which is very similar to the one from GR, apart from this factor here. And one way of interpreting this is to say that this rho over FQ is an effective potential. So this is the modification from F of Q theory. The same Poisson equation was also found in cosmology using different assumptions. So my next question that I'm trying to answer is that if this modification is valid for any kind of connection. Because here I use a rather specific one. And as I mentioned before, I want to apply this to the stars and possibly constrain the theory. So just to resume the talk, I talked about the geometric unity of gravity, and I focused on the symmetric and parallel coordinate because I wanted to talk about the F of Q theories, which are a modification of this theory. And I also talked about the equations of motion of this theory and apply the field, the weak field limit to those equations for a particular choice of connection. And I got my modified Poisson equation. So that's all for me. Thank you.
For a clear talk and Professor Ali, we have time for questions.
Thank you for the very clear talk. Two questions. The first question is that it seems that your Poisson equation involves some different effective Newton's constant. You injected K over G. So this means that all the predictions for the constraints or variation of the Newton's constant apply in this theory, or there are some other constraints that want to apply?
Well, I haven't looked at that from that perspective, actually.
Okay, and my second question is there any f of r equivalent to this f of q theory? That, for example, if you have just q, it's equivalent to relativity. So if you have f of q, one could wonder if there is some f of r which is equivalent to this f of q.
Also,
Is there some transformation that can take from f of q to f of r?
in general, no, because the extra terms, yeah, this extra term will have nonlinear contributions. So you must have like f of q equal to f of r plus, some terms of like this, some terms this times q or some, so there is not a direct relationship.
Just one question, so as far as I have read, in GR when you perturb the Schwarzschild metric, you get sort of two perturbations, two plus and cross polarization of the gravitational waves. So if you perturb Schwarzschild metric with in f of q gravity, do you still get only plus and cross polarization, or there are other modes of gravitational waves?
Well, I honestly don't know much about this. But, if I remember correctly, at least from Q, you don't get any new polarization. So for f of Q, I'm not aware of it.
Two questions as well. First is how the non-metricity is coupled with the fermions in the papers about Dirac equation on the background of non-metricity gravity. And second question, is it possible to formulate the non-metricity gravity in terms of the violation of the tetrad postulate instead of non-metricity, and if it would be an equivalent formulation, or it is different?
For your first question, so you want to know could you repeat, please?
If how fermions would be coupled with the non-metrical gravity?
Usually we assume that the matter is coupled only with metric, not connection. So in that case, there won't be coupling between the non-metricity and matter, only with metric.
And second question was if you can base the analog or maybe equivalent of non-metricity gravity postulating the violation of the tetrad postulate instead of the non-metricity.
Mm-hmm. Yeah, not aware of it.
Okay, if there are no more questions, let us thank the speaker.